Okay, so I think it's time to start adding some more instructions now. I thought maybe I'd start with the LEA instruction, so load effective address. So if we look for it in the manual here, we've got LEA. And it's a pretty simple instruction. There's only one opcode for it, so we've got 8D here. It only accepts register destinations, and it only accepts memory sources. And the register destinations start from 16 bits. So it seems like we can put in a few assertions into a LEA function and then just use the same logic as we're using in MOV. So what I might do here is basically split off the all of the logic that does ModRM, SIB, displacement, immediate encoding, put that into its own emit complex function, and then just have each of the instruction functions call into that once it's selected its opcode, done any assertions and any sort of operand manipulation they need to do. So we'll start with some test cases, and if we go to generate a test, I think if I just get all of the MOV instructions that have a memory operand on the in the source position, so that's going to be all of these ones, for example. We'll take them over to test cases here and paste them in. There's some restrictions here, so we can't use byte destinations, so we'll remove all of these. So let's see, we've got, let's look for AL in here. We'll remove all of these ones because these are all bytes destinations. All the way down to here. I can't see any more. And I think that should be it. We'll try and assemble this. So we've got test cases.asm, output to test cases, that all looks fine. Disasm B64 test cases. We'll take all of these and we'll put them into the generator test cases. There's one up here where I need to fix the formatting. Okay, so this is the expectation. Oh, these are MOV. I need to change them to LEA. So let's do LEA. NASM, endisasm. Okay, let's take all of these test cases instead. Okay, we'll fix the formatting on this one. Get rid of this, take the expectation, move it past the instruction here. Okay, and this is the test case. So for all of these test cases, we need to run a LEA instruction. I'm just going to clean up some of this syntax a bit first. So if we've got W plus and W. Okay, oh, I see, okay, so we've got rel and then a completely different hex number to what I actually put in. So I guess the disassembler is just showing us the actual target address as opposed to the displacement that I want from the instruction pointer. So I'm just gonna change these. So we'll change any rel followed by a 0 to be rel dollar plus the actual value. So this is 7f, ff, ff, ff. And actually, since I'm changing the syntax anyway, I may as well just replace all of these with RIP, because that's actually what it is. Then I need to call LEA in here if the mnemonic is LEA. So we've got LEA, and then let's go to MOV. Okay, so MOV over here is... So first we have opcode selection, and then after this point, the rest of it is just, ModRM, SIB, displacement, and immediate. So we'll call this one emit complex, and we'll take in an opcode, which will be a byte. So this MOV1 can select the opcode and then call g emit complex, passing in the opcode, the size, the destination, and the source. And then we'll do the same thing, but for LEA instead. And here opcode was actually, I think it was 8D. So we can get rid of all of this, and we can just put some assertions in here. So we'll just say, for example, if the size is byte, we'll panic with LEA can only be used with size of bytes, size of word, dword, or keyword. If the destination is not a register, LEA destination must be a register operand. And if the source is not memory, then the LEA source must be a memory operand. So that takes care of the assertions. So let's just see what happens here. Okay, so we've got an unknown scale. This is because I'm... okay, let's go and have a look at this in the test cases. So we've got EAX plus EAX. Is that what it was? Oh no, RDI. RDI plus RDI. So it looks like the problem here is that in the multiply by 1 case, because I don't have, when we do the cut on the asterisk, num here is going to be an empty string instead of 1, so maybe I can just leave this as empty string here. Okay, that seems to have done it. And then the rest of this is just failing on a bunch of these tests. And I think... Let's go have a look at the generator. So the destination must always be a register. And the source must always be memory. So this is going to true, which means that this direction bit is being set. So I think so there are exceptions from what I remember in the manual for quite a lot of instructions that use two operands. The direction bit is used to decide which way is RM and which way is R. So which way is the memory, which way is the register. But for something like LEA, which can only be used in one direction, the direction bit doesn't make any sense. So I think what we'll do is we'll switch on the opcode, and for any exceptions, we'll just add them to this case here. So this one is 8D, which is LEA. And in these cases, we want to do nothing. But in the default case, we will set the direction bits. Okay, so that works. That's LEA done. Since that was so quick and easy, I guess I'll do a couple more instructions. Maybe we'll have a look at add. I'm going to need to be able to add numbers. So here we've got a few special cases where the register destination is one of the A registers. But beyond that, it looks like it's basically just an opcode of 80 or 81 with the extension 0. So we've got a /0 for all of these. And then it seems like, yeah, so for example, we've got opcode 2 here. This is because the direction bit will be set when these flip around. Okay. So we'll have to do some special casing for these A registers. But beyond that, I think it's basically just 80 and 81. So let's just try this out. Maybe 0 here actually as well. We've got RM. Okay. All right, well, let's just try this. So we'll take the MOV test cases again. Since add is pretty similar to MOV as far as the operands it can take, or maybe even exactly the same. So we'll get to test cases. Let's just get rid of these LEA ones and put these ones in. We'll just change all of these to add instead. We'll do NASM. RIP not defined, yep, that's true. RIP, I'm actually going to change back to rel dollar. Okay, let's try that again. D-word okay, so this is probably the immediate case. Yeah, so MOV is a special case where it can take a 64 bits immediate, but add can't do that. So then we got disassembly. Okay, let's take all of these cases. We'll take them to generate a test. Okay, let's just put them in here. Fix some of this formatting. Okay, and then we'll just take all of these, get the expectation, put that after the instruction. Do we have any rel? Yes, we do. Okay. This is a little bit annoying, but we'll just fix these again. So these ones are going to be RIP plus OX. Are these all the same size? I think they probably are. We'll do OX7. Oh no, this is going to be 7F. FF, FF, FF. Okay. And then we need to add an add call into here. So we'll do add. This is the same, size and then 2 operands. So here we need add. This is going to be pretty similar to MOV. And actually, looking at MOV, I could probably change this around a bit, but we'll do that after add. So let's put add up here. So we've got add. Now, if the source is a register or if it's memory, let's see. If the source is register, then we want 0. If it's memory, then we'd be 2, so that's just setting the direction bit. So we'll say that if it's source or memory, then we do 0 as the opcode. that may get the direction bit set. Then we got yeah. So if it's not bytes, then we add one to the opcode. If it's immediate, then normally it would be 80. And then if it's not a byte, we would add 1 to that still, so we would get 81. So that's correct here. Then we've got extension 0, which for add is also correct, that's extension 0. And then we've got some special cases, which are the sort of assuming A registers. So this is an implicit A register where the instruction is going to be a bit shorter. So in those cases, we can use 4 and then add 1 for no, for something that's not a byte, basically. So if it's immediate, okay, maybe we'll just do this and see where it fails for the special cases. These ones are actually going to be, I think this one. If the source is immediate, yeah, so if the source is immediate, then it's always RM. So we'll get rid of this check up here and just do the generation like this for now. And we'll see what happens. Yeah, so they all pass except for these special cases of the A register being implicit. So in these cases, we basically end up with a shorter instruction because we don't need the ModR M. So if it's an immediate and the let's see, if it's immediate and the if the destination is register and the destination is equal to AX in some way, then in that case we would want the opcode to be 4. And we don't need an extension in that case either, so this is only for the RM case. So here we've got the 04, but we've still got F8. So I think I'm going to need to add another flag here to explicitly say that we don't want a mod RM. So we'll say no mod RM here, maybe. And we'll go over to the flags and just add no mod RM. I don't know. I guess we'll put it below no base. So in the case of extension right now, let's see. There is a case where we skip the mod RM. So that's if the destination isn't reg part of opcode. So we'll say that if it's not no mod RM, then we'll do this. And up here where we do the reg part of opcode, we'll just alter the RM. So we'll say, so we're doing the check on destination no mod RM. So we'll do dst info and we'll just add no mod RM into this case as well. No mod RM. Well, that's broken a lot of them. So oh, this is the case where yeah, okay, we don't want to do it on that one. We want to do it on this one. Okay, that's past all of them. So the changes that I can do here, though, is that this not byte thing is only ever incrementing the opcode, so I could just do that down here. That still passes, and I can probably do the same for MOV as well, because this only ever increments by 1. Oh wait, one of these incremented by 8, actually. That was this one. So if the opcode is B0, we should increment by 8. So if it's not bytes, we'll do this, and that increment by 8 was also the byte thing. So we'll say if opcode is this one, then we'll increment by 8. Otherwise we do just an increment by 1. Okay. So let's add, and then since we're doing add, we may as well just do sub as well. So let's go find sub. So we've got sub down here. And this is the same thing as add, but we've got an extension of 5 instead. And we've still got the implicit A exceptions here. But these ones are using 2C instead of 4. So we'll just copy add over here, and we'll make sub as well. So the register one starts with, let's see, this was if the source is register or memory, then we're going to start with 28, and then with the direction bit set, we go up to 2A. So 28 is where we start with this one. Then the implicit A register is 2C. And the other one where we've got an immediate is starting at 80 like the other one, but the opcode extension is actually 5 in this case. And then we've got the same thing where if it's anything but a byte, we'll just add 1 to the opcode. So we go to generator tests, and we'll take all of these add ones. Take them over to test cases. And we'll change them all to sub. And RIP should change to rel $. Okay, so we'll do nasm, endisasm, and we'll just take all of these. And since they're all in the same order as the add ones, I think what I'll do is I'll just fix these bits of formatting here. I'll just take the expectations. Copy all of the add ones. And then we'll just go down and change all of these to sub instead. So go down to the bottom. Change these to sub because they're all the same, but just change the expectations there. So go test. Let's see what we've got. Oh, unhandled mnemonic. Okay, yeah. So we need to add the sub mnemonic here as well. That passes, but just to check, let's change this extension to 2 or something. Now they all fail. They're all failing on the sub ones here. So we'll change that back to 5. Go test. That's all fine. Okay. I think that will do for now. Maybe I'll look at some other instructions that require one operand, like mul or div or something like that next.